So in the old days of third-party cookies and mobile device identifiers, the user agent, that is the web browser or your mobile operating system, basically gave out a user-level unique ID to every app and website that you visit. And while that enabled a lot of really interesting things to be built, it wasn't fantastic for user privacy. Because if those apps and websites are willing to share data with one another, they can more or less recover someone's entire browsing history. So these days, in the interest of providing better privacy protections to users, all of the user agent vendors are moving away from that. They're deprecating third-party cookies and mobile device identifiers and other approaches that could be used to enable widespread tracking. But there's a lot of systems that are going to break as these changes are made. And one of those things is ads measurement. When a business spends money on ads, they'd like to know how many times someone made a purchase as a result of seeing those ads. So imagine a business spends $1,000 on ads and that leads to 345 purchases on their website. That's what they want to know. That's the information that they'd like to get out of the end of this system. So in principle, that aggregate output doesn't necessitate knowing individual user browsing histories. And if there's some way that we can build a system that only produces that aggregate output, it could still be fit for purpose. So we're trying to find a new path forward. Through standard setting organizations like the W3C and the IETF, people representing browsers, users, and businesses are all coming together to see if we can put together a new way of doing private measurement that does a really good job of protecting people's browsing histories and keeping that private. There's a whole bunch of different proposals that are currently on the table. Google has proposed the aggregated reporting API. Apple has proposed private click measurement. And most recently, Mozilla and Meta co-authored a third proposal called Interoperable Private Attribution, or IPA for short. All these proposals have a lot in common. They all seek to provide aggregate measurement with a really high degree of privacy protection for users. And all of them involve shipping new APIs in web browsers and mobile operating systems to make this possible. They just differ in the mechanism by how they achieve those goals. So in particular, I've been working on the IPA proposal, and I'm going to tell you a little bit about how it works. IPA is based on processing secret shared data within a multi-party computation. In particular, what we've proposed is a three-party, majority honest MPC that would provide malicious security with abort in the presence of up to one corruption. So in our proposal, user agents would no longer be giving out these match keys in the clear. Instead, they would give each app or website a secret shared, a differently randomly secret shared match key that's encrypted, with each share encrypted towards the different helper parties running the MPC. What this would do is allow apps and websites to collect these identifiers that are useless on their own, that couldn't be joined or used in any way outside of the particular multi-party consortium. We've developed a zero leakage MPC protocol that allows events originating from the same match key to be joined up together, and for conversion events like purchases to be attributed to ad impressions or clicks that had previously occurred in time. It's a really flexible system that supports a whole bunch of different use cases, and even different attribution heuristics are possible. But most importantly, we think it does a fantastic job of protecting people's privacy. In this proposal, the user agent vendors, that is the web browser companies, they're in a position to select parties that they trust to operate the three MPC helper nodes. However, even in the event that something goes wrong, and one of those parties is, compromised by a hacker or compelled by a government to hand over their servers, user privacy is still preserved. And even if one of those helper parties were to deviate in arbitrary ways from the protocol, the honest parties would be able to detect the aberration and abort with no private user data leaving the system. So let me just sort of give you the 10,000-foot perspective of how IPA works. There's a couple of different stages, and I'll walk through each of them. So the first step is that the businesses who are collecting data about interactions on just one app or website take their data and they share it with other websites. So if you're a business who's buying ads and you have some information about what people bought on your website, and you bought ads from a different website, the information about which encrypted match keys saw ad impressions are sent to you. Then secondly, you take all the information about these rows of data corresponding to ad impressions and purchases, and you sort them by timestamp. Once all the data is sorted by timestamp, the business can then secret share additional information. So they have data about what ad was shown, or if someone made a purchase, how much money they spent. So they can secret share that to keep it confidential from the MPC helper parties. Finally, they submit all those rows to the helper party consortium, which performs this zero leakage protocol. What it first does is it sorts all of the rows by match key, this encrypted match key that they've never seen themselves and the helper parties themselves never see. Fortunately, there's been a lot of incredible research recently from the academic sector on how to do efficient sorting in MPC. And we're incredibly grateful, specifically to Ryu Kikuchi, who's been helping us a lot with understanding the advances that have been made in that space. So once all the rows are secret shared and sorted, we can perform what we call an oblivious attribution algorithm, which compares rows to ones from people who have the same match key and which occurred previously in time. And we have a number of proposals for ways of doing different types of attribution heuristics, whether it's last touch or multi-touch or exponential time decay, whatever you might want to do is theoretically possible in MPC. Next, the helper parties cap the maximum contribution that an individual user can have to the output. This is really important for providing a differential privacy guarantee to users. Then all of the results are aggregated together based on some kind of breakdown key that was decided by the report caller and then secret shared before being sent in. And then some amount of random noise is added to each of the breakdowns to provide that final differential privacy guarantee to users. Finally, this noisy histogram of data is released to the API caller. The differential privacy guarantee ensures that you can't tie this back to a specific person. This aggregate information can't be linked to learn what a single person in particular has done. Even if you run multiple similar queries and try to difference them against each other, user privacy is still protected. Now, in order to make that happen, we have to manage a privacy budget. So each time a report caller issues a query, it subtracts from that app or website's total privacy budget. And once that weekly privacy budget is exhausted, you can run no more queries until the next week begins. In this way, we have a really, really good control and understanding of exactly how much information leaks over a given period of time. And we can provide users with this strong guarantee that absolutely no way can more information than X be learned by a specific app or website per week. So, as I mentioned earlier, it's a flexible protocol. We have a lot of work to do. We're trying to figure out how to tune it. And that's the next sort of steps that we're working on, is to improve the efficiency. As the API callers themselves are going to be having to pay for each query that they run, we are trying to minimize those costs. We anticipate that communication between the nodes is going to dominate the costs as opposed to computation. And so we're trying to optimize for protocols that have a minimum of communication. In particular, the sort operation will likely dominate the total cost. And so we've been focusing primarily on optimizing that sort by match key. As I mentioned earlier, the researchers from NTT have been incredibly helpful in helping us understand the recent academic advances in that field. And that's a little bit about how IPA works.